Hello, my name is Cassie Jang, and I am going to walk through the channel impulse response tutorial that will produce a impulse response and potentially some multipath separation for a link on the Powder wireless network testbed using the Shout measurement framework. So this tutorial was originally created for the CyberPowder Fellows 2025 program, but it can be run through individually using either this Google Colab or the Git repository that has all of the necessary files and the same Python notebook. So to start, we're going to have to create a copy of this read-only Google Colab. And if you're going to create your own experiment and run through the tutorial steps to collect your own data, you're going to want to instantiate an experiment so that it's ready when you are ready to use it. If you're using the data provided in the Git repository, then you don't need to worry about that. So to start, we're going to import our packages. And then we're going to run our functions. And our first step is going to be to make an IQ file using PN codes that are produced using a linear feedback shift register. And we're going to choose a number of stages between 7 and 11. And this is going to be associated with the length of the PN code by this equation given here. And we're going to choose our end stages in the code. I'm going to choose 9. And these other parameters, samples per chip, sample rate, alpha, they can be all modified on your own using larger bandwidth in order to see more multipath separation or smaller side lobes, etc. But for the purposes of this tutorial, we're going to use the parameters given. And this code is going to give us the taps that we need for our PN code. So we're going to use these taps, and the idea that our PN codes, both the in-phase and quadrature, need to have a starting initial state vector. And this state vector is going to be the same number of elements as the number of stages we chose, which in this example is 9. So we're going to pick a sequence of states, starting states, that is not all 0. So typically it's mostly 0s and 1, 1. And do the same for the quadrature. And use a different starting state vector and a different taps. And we can run this to make our PN code. And we need to specify our IQ file name. And that's going to generate the IQ file that we're going to use for our experiment. So this can be downloaded so that we can use it for our experiment. And then we're going to walk through the instructions on how to run your own Shout experiment. This assumes that we already have instantiated our experiment, and we have done that in this case. So to start, we're going to copy the commands and the IDs from the experiment list view, which if you're on the experiment page is this table down here. And we're just going to copy the SSH commands as a comma-separated list with no additional spaces. And do the same for the IDs, which are just going to be for the compute nodes, not the orchestrator. And then we can run this, and it will give us the commands that we need to run in order to run our experiment. So first, we're going to secure copy this IQ file that we made with the PN codes to all of our nodes in the experiment. And we're going to do that on a terminal window on your local machine. And then we're going to copy the commands listed here to SSH into the orchestrator for 2 different sessions. So I have my 4 windows up here, and then both of the clients. So now we have 2 orchestrators and both clients, honors and hospital. So then we're going to need to modify our JSON file, which give the experiment what parameters we want it to run. So if we play the code, it's going to tell us what parts we need to edit of this JSON file. It's going to tell us to modify the frequency, where we specify the IQ file name, the clients, and tells us to modify the clients to be our nodes. And if you're using dense deployments, to change the gains. So back in our local host, we're going to modify the JSON file. And we want the TX frequency and the RX frequency to be within the reserved range that we have, and we also want them to match. And we're going to save that. And then copy these commands to our local machine to secure copy the JSON file to all the nodes. Next, we can actually run the shout experiment. So we're going to start with the start orchestrator command in the first orchestrator. And that's going to start a listener. And then we're going to start the clients. And then once these show that they are waiting for commands, we can run the second orchestrator session to run the experiment. So see, this says waiting for command. We can go to the second orchestrator session and run the experiment. Once the orchestrator returns the command prompt, we're going to change directories to where the data folder is created. And we're going to zip this data folder so that we can easily copy it back to our local machine. Now we have a data.zip, and we can run this secure copy command to copy our data.zip to our local machine. And we're going to do this on our local machine. Then we want to navigate back here and we want to upload, and we're going to unzip it. And then we can run through our cross-correlation and channel impulse response using this collected data. If you didn't run through the experiment and you're just using previously existing data, you can skip straight to uploading the data.zip and unzipping it and continue from here. So we're going to run our functions, and we're going to copy the folder name after we've unzipped it and paste it here. Run our channel impulse response functions. So these cross-correlation plots are showing the cross-correlation of the original transmitted packet with what we received back after the experiment. So in each of these plots, you can see that we have found our original transmitted packet 3 times with some noise and potentially multipath in the background. So for this, we're going to pick one of our plots. For the purpose of this, I'm going to pick 0, which is this first plot. And we're going to zoom in on it so that you can see the peak closer. This is the plot that I chose. And I'm going to zoom in to around 20 microseconds. And here you can see the cross-correlation peak where we found the transmitted packet at a 820 microsecond delay, and potentially some of these side lobes and or multipath that we might have found in the link. Different links and different PN packets and different repetitions are going to look slightly different, but this is about what we should see with our channel impulse response. The side lobes and this ringing is a result of the square root raised cosine shape that we use when modulating and demodulating the signal.